that connects string theory to particle physics. And in particular, in this connection, I would like to focus in addressing particle physics. Yes?
The best thing is to start from this one.
Oh, okay. Oh, it's the biggest. Okay, yeah, we'll see. Okay, thank you. So addressing particle physics with D-branes. And in this effort, I'll include both how much we can learn about vacuum of string theory with D-branes, both from perturbative perspective and non-perturbative effects. So let me just mention, I handed out some very rough notes that have more of an emphasis on the second part of my set of lectures, but I thought it's still probably useful to supplement some of the notes you may be taking or the ones that will hopefully copy after its lecture. Okay, so it's really more like a rough thing that you may want to use as a backup. And it has really more emphasis on the second part of my lectures. Okay. So the particular topic that we want to focus on is dealing with string theory and how it can what it can tell us about specific aspects of our world, which is particle physics. So this is the physics that we hope to test beyond what we already know at LHC. Okay. But also another set of aspects that we want to derive from string theory is also possible cosmology. In particular, aspects of finding out more about implications from string theory, for example, for string-motivated inflation. Well, in this effort, we want to ask ourselves, how much can we derive from string theory? Okay? So is our hope to get really unique string solution that would have all the predictions for particle physics, and hopefully also for cosmology? Okay. I think that was even at the early years of, first string revolution in mid-'80s, probably a too ambitious and probably not realistic goal. Okay. In part, so in terms of unique predictions of string vacuum. In part, there are probably two issues here. Okay. One is the issue of whether our construction of string vacuum from string theory is determined dynamically to be the unique vacuum, or whether there is anthropic principle involved. Because really at this stage of our understanding of string theory, we really don't have a unique way of saying this is our preferred solution to string vacuum because of the lack of dynamical principle. So this is more of a conceptual issue. Okay. The second issue, actually even that has to do really more with the technical issues. Okay. The second issue is really the fact that the way we can really explicitly determine four-dimensional string vacuum is only in very special cases. So due to lack of developed techniques, so only a small subclass can be addressed explicitly. And so it's really more of a technical issue, though, you know, it's in this direction, okay, that over last, since mid-80s and then during the second string revolution in mid-90s, where we have made a lot of progress, and we have developed a lot of techniques by which we can really explicitly calculate features of the four-dimensional string solutions. Dynamical issues, I think we are still where we were at the early, you know, during the mid-80s. I don't think we could make, at this point, new input as far as the dynamical choice of the vacuum. So in these lectures, my lectures are actually, in that sense, somewhat less ambitious compared to this lofty idea. Okay? So what I want to really focus on is highlighting specific frameworks of string compactification where we could get certain generic features of types of particle physics that we have. So it's less ambitious. So in particular, we want to deal with the framework so as we'll see, different type of string theories where we could have specific generic features of particle physics that we can get. And then within particular choice of four-dimensional string theories, the second thing that we can be ambitious enough is, in concrete examples, explicitly calculate determine spectrum, so light spectrum, because that would be our particle physics word. And another level of development that we have is not only the spectrum of particular explicit four-dimensional solutions, also couplings. And not only in perturbative theory, also with non-perturbative effects included. Okay. Yes, yes. Yes, please.
So when you say generic features of particle physics, do you basically mean the gauge rules that?
Yeah, in particular, specific, I'm going to choose different frameworks, okay? Actually, I'm already announcing which framework. I'm going to be even more specific about the framework, okay? So I'm going to choose specific, so maybe, so I should say specific framework within which we would get certain generic features, okay? So you know, this is somewhat less ambitious in terms of unique predictions of string theories, but from different frameworks, different four-dimensional solutions of string theory, frameworks of solutions, we get certain features of particle physics. And from this generic different frameworks, we can learn about specific properties. Okay? Not that this one is the one that string theory predicts, but we see how much we can learn about it within frameworks, okay? And then, yes. Well, you see, yeah, the point is we would like to see what is there really a unique ground state, okay, of string theory. We don't have it in our context. You know, the hope was that string field theory may be able to tell us. Okay, at the level at which we are in understanding string theory is really at the first quantized level. Okay? Solving equations of motion and saying they are consistent, our solutions are consistent. But I mean, this is ambitious with lots of effort in, but I don't think we have a great insight. Okay. Any other questions? Okay. So this is basically the idea behind, you know, of the what I would sort of call subject of string phenomenology. Okay. So this is how far we can get within this context. String phenomenology. Now, the part that I'm going to focus in my set of lectures will be really the aspects of particle physics. Okay. So basically, referring to the issues you were mentioning already, I want to deal with the gate symmetry of particle physics, the spectrum, and the coupling of particles. So of low states with, you know, at energies that we are at very low energies. Okay. The issues of cosmology, which naturally actually probes aspects of complications of string theory, in particular moduli stabilization. Very involved subject, very difficult subject. Okay. But in these lectures, I will not talk much about it. Okay. So in this sense, in part, because I know much more about that one. Okay. All right. So the idea is basically to deal with the spectrum and couplings of light particles that we get from string theory in 4 dimensions, okay, and hopefully see how close we can connect it to particle physics. So let me remind you that what we are after now within these different 2 frameworks, okay, I mean within this less ambitious approach, okay, we basically want to see how close we can get to describing features of particle physics. Okay? And so the cornerstone of particle physics, the cornerstone of particle physics is what we call standard model. So I guess I won't remind you much of it. I won't waste too much time on that. But let me emphasize 3 key points, okay, that we actually want to reproduce from string theory and are core of describing standard model of particle interactions. Okay. So first one is the fact that interactions of elementary particles are based on non-abelian gate symmetry, and for standard model, this is SU3 color cross SU2 electroweak, which is based on SU2 cross U1 symmetry, and is basically a feature that is associated with what we call non-abelian gate symmetry. The second key feature that we observe in the standard model of particle physics is the fact that we are dealing with light fermions. Okay. In particular, we are dealing with quarks, which appear in left and right handed representations. And so in particular, they are typically in certain bi-fundamental representation under strong and SU2 electroweak symmetry, and then they have fixed hypercharges so that we get a correct electric charge after we break electroweak symmetry. In any case, so this charge is in this case plus 1/6, and then we similarly have right-handed quarks, which are in 3 bar, but they are singlets, and under hypercharge they have minus, let me see, in this notation is 4/3, and similarly right, 3 bar, 1. So let me use this notation for representations, and then plus 1/3. So we have quarks, and we also have leptons, and leptons also appear in as doublets under SU2 symmetry, singlets under SU3, and then they have hypercharge in that way, defined in this way. And so similarly, we are dealing with right-handed electron, which is singlet, but has charge plus 1. And without loss of generality, sometimes we can add additional right-handed neutrinos, which are of the type total singlets under all symmetry groups. Okay? Yes?
Why there is minus 4?
4/3? 2/3, right? Yes, thank you. Right, it's 2/3, and depends. In particular, recall that electric charge, Q electric, after breakdown of electroweak symmetry is equal to the T3L. So this is diagonal generator of C2L plus QY. The charge, I'll put that in this convention. So those are actually guys that before electroweak symmetry breaking are actually strictly massless. And so we have to hopefully explain why from string theory we get really such light, extremely light so-called chiral fermions. In addition, we also, in the context of supersymmetric standard model, we expect to have also Higgs doublets. Actually, they come, the standard model can get by just with a single Higgs doublet, but in the supersymmetric ones, we need two. So if I do that with my convention, I'm a little bit, I think it's 2/1/2. Thank you. Okay? And we often refer that to up and down. Okay, so this is the second feature of standard model, which is based on chiral fermions. Okay? Yes. Yes.
What sense do you mean by light fermions? No top part.
Right, but this is all at very low energies compared to energy associated with gravitational physics and string physics per se. Yeah, everything is really light here. So because basically string scale associated with string theory will be much bigger than TeV in generic case. Though even in this lectures, I'll get to issue when this is comparable. But okay, and so so we are now dealing with so this is the first feature, this is the second feature, and then there is the third key feature of the standard model, which is that these families So let me just to keep it on the same blackboard. So this the chiral fermions actually appear in 3 identical copies. So the third feature is family replication. So actually, experimentally, we know that we have 3 copies, 3 families of quarks and leptons. Of course, we know even more, right, about a standard model. We actually know how those quarks and leptons couple to Higgs field, okay, via certain Yukawa couplings. And since we know the masses of quarks and leptons, we can actually indirectly from the standard model argue about the size of specific interactions. Okay? So in particular, if we are dealing now with the couplings, we expect that now at this effective theory of that describes particles of the standard model, there would be an interaction of the Yukawa type between, let's say, the quark doublet, the right-handed quark, and the Higgs field with certain coupling H. Since those things come in copies, in particular, if this is the third family, this would be the largest Yukawa coupling. Okay? So the things that we should be a bit more ambitious in describing from string theory is not just this non-abelian gate symmetry structure, chiral fermions, original chiral fermions, and family replication, 3 copies of families. But we also should hope that at this stage we have techniques developed for which we can actually calculate these couplings. Okay. And hopefully within specific framework have predictions for these couplings. Okay. Any questions? Okay. So my goal will basically focus on the issues that I underline. I'd like to choose specific frameworks in which I would demonstrate the appearance of standard model-like symmetry or non-abelian gate symmetry, the appearance of chiral matter, the replication of matter, okay, and to be even more ambitious, the issue of couplings themselves. Okay. Yes. So as I said, it's related to issues of modular stabilization, but I will not address how these moduli are fixed per se. Okay? So it's actually choice in modular space.
So it's around some point.
Right. In some cases, you don't actually have enough moduli, and you can actually make more firm predictions. Okay. Okay.
So you're saying that whatever physics that fixes your moduli, you say is not going to affect?
No, it will in principle affect.
But
Okay.
Not just that depends on the moduli, but that in addition to that dependence, there will be dynamics, right?
Well, you see, in general, as was raised, these couplings, unless one is in very special isolated points in moduli space, depends on moduli.
Yeah.
Okay?
To get rid of the moduli space, you need to, right now if you have a bunch of extra light fields, you need to do something.
So, right. So in this context, we have to, first of all, it's a technical thing to be able to determine dependence on moduli, okay, of these couplings that are associated with the charge matter in the theory. Okay. Now, in parallel, one always has to worry, okay, about moduli stabilization, okay, that we hope will come from additional things that we put in the system.
But will
Okay.
it change the functional form of H of T?
It can change it because this is function of moduli, right? It will fix it once we fix this.
But the functional form, you say, is the same.
Yes, of course. That's the thing, yeah. But we don't know, so for example, if I choose particular value of moduli of the compact device space, I would calculate this as function of this modulus. Why it is chosen there? Why this VAV is chosen to be what it is, okay? It's an issue on a problem of modulus stabilization. We can come back to that when I start talking about couplings. But let's talk about the first part that is rather insensitive to issues of modulus stabilization, okay? All right, any other questions? Okay, so this is the less modest goal, within specific frameworks to at least reproduce those issues and then turn to more complicated issues of couplings. We'll deal with that in the second part of my lectures. Okay? So now we have a number of frameworks. Okay? So let me talk about different frameworks to justify which one I'm going to focus on in this set of lectures. Okay? Basically, frameworks have to do with where we have actually techniques where we can calculate things. And those are basically corners, different corners of M theory, okay, where we have explicit perturbative techniques to do calculations. Okay. So corners of M theory. So basically we have corners of perturbative string theories. So those are perturbative string theories. I could draw this famous. Okay, so let me draw it anyway. What is the issue? See if okay. Now you see that this is suitable for men's shirts because it goes okay. Anyway, so let's talk about different corners of M theory. It's there, right? Once I get closer, it's not a... Okay, so let's go on. So we are dealing with heterotic string corner. Actually, two of them, E8 cross E8, and heterotic SO32. With some discrete issues there. And then we are talking about different types of superstring theories. So heterotic corners are perturbative string theory that is basically a hybrid one. In one sector, it's superstring theory. In the another right-moving sector, there is a bosonic string theory, which is reduced to 10 dimensions in such a way to reproduce gauge bosons with these features. Then we are dealing also with type 2A and type 2B. So let me call it type 2B and type 2A. 2A theory, and those are specific superstring theories, closed superstring theories, and then there is a pure open string theory, type 1. And then typically we draw also 11-dimensional supergravity, which is another limit of M theory. And by now we heard a lot about possibility also going inside here and treating string coupling of type 2B theory in terms of F theory. Okay? So as perturbative corners, Okay, we have specifically focused in the past on heterotic theory because a priori already in 10 dimensions reproduce for us reasonable, potentially interesting asymmetries that could be related to grand unified theories and potentially could deal. We could deal successfully with the standard model. So that was a focus for mid-80s till about mid-90s, and of course it's still continuing because we are developing further techniques here. Okay. But really, the direction that after the second string revolution that gained a lot of attention and ability to really put some modern perspective on particle physics came with the advent of D-branes. And actually also the way we couple superstring theory to open strings via the introduction of D-branes. And basically, this is the new corner in which we are focusing to try to derive particle physics. Okay? So those are the corners where I'm going to spend most of the time. Okay? So those are the corners here will be basically type 2A, type 2B. Maybe I'll say something here about that too. But it's basically the corners, the frameworks, okay, where we introduce D-branes. And in particular, among those frameworks with D-branes, I'm going to spend most time on type 2A. Now you'll ask me, why this corner? Why spending all this time getting particle physics out of this corner? The reason is that actually this framework turns out to be very geometric. Okay. The features of the standard models will be described in a rather geometric way. Okay. And even couplings will have some of its origin described in terms of geometry. So this is a geometric phase. It's geometric. That's all I want to say. Okay? And that's the main reason that I'll focus on this aspect. Yes, but 2B will become less geometric. Those would be certain bundles, vector bundles on that. And here I'm going to talk about cycles, special Lagrangians, and something that I could draw pictures, okay? Because I can draw pictures, and those are introductory lectures to particle physics with D-branes. I'll focus on that. Okay. But since we know how dualities work, that is rather, at least in principle, at least from type 2A to magnetized branes, we can go in a very straightforward way. The full type 2B theory, it's harder, and that will be another intriguing way to deal with this whole aspects. But that's a lot of it is fresh, including yes. Sorry.
What was your comment about heterotic framework?
Well, heterotic framework is primarily based on closed string theory itself. Okay. And it's less geometric. Okay. Yeah. Why it was? Why? First of all, the focus prior to second string revolution was on this heterotic corner. This stuff was backpedaled. That there are other theories. Okay. In part because the gate symmetry of this closed string theory already was rather suggestive of being connected to grand unified theories, because the 8 is subgroup of, E6 is subgroup for 8 and was one of the possible grand unified groups that you could keep connecting down. So, and the really another real problem why those theories were neglected has to do with the fact that we didn't have techniques to address D-branes there. Okay, so it wasn't till Joe came up with approach to study more general open string backgrounds that allowed us to study that. Actually, it was very inert, and there were even no-go theorem that you cannot get a standard model out of this thing, but that had to do with not allowing for general boundary conditions of open strings. Okay, so we were stuck. We were focusing on this aspect. Okay, but I will not spend much time except only maybe connecting a bit, contrasting some of the features there with the features that we have with the D-branes. Okay, so with this slow, introduction, this is the framework that I'm going to focus on. Okay. All right, so what is the rest of my lectures, okay? Oops. Those are the, this is it? Okay, yeah, but yes. So I should, that's, okay. How does that work? The other one is hidden. Okay. No. As I said, it's less ambitious effort. We try to address things in different frameworks. I'm going to focus on this one. As I said, we don't have dynamical reasons, right? We are also only in the corner when we have a technique, right? But it's sort of intriguing thing that can give us a lot of generic predictions. I don't know whether nature chooses this one, but it's intriguing feature. I'll try to maybe in some instances contrast results there maybe to results in other corners. Okay. So the outline, okay, of what I still want to tell you in the next 35 minutes, 40 minutes or so, okay, is first. So we are dealing with open strings and D-branes attached to them. So what I'm hoping to get to is addressing now the spectrum of four-dimensional theories with D-branes. And as I said, beyond non-abelian gate symmetry, when we turn to chirality and family replication, I'll turn to type 2A theory and a framework with D6 branes that will turn out to intersect in internal space. At a number of points. Okay. So I hope at least to give you that part in the next 35 or so minutes. Okay. And then, in the second lecture, if you have the stomach and I have the stamina, I may go to more detailed conformal field theory quantization approach. to physical states, to determining physical states, in particular massless states in the background or intersecting brane. And then, as a follow-up, as a continuation of this, after we so conformal to intersecting D-brane spectrum. So the next thing that I want to then go to is actually to an important issue of what we call global consistency conditions and anomalies that we have to address in this case. So that would be one part, and the second part would be global consistency, the so-called tadpole cancellations. Also, more general issue of anomaly cancellations. Actually, that will be also, some of it will be preparation to study the instantons in the later lectures. Okay, and so then in the this will also, in concrete context, bring us to the issue of orientifolds. So in the third lecture, I hope to then deal with some concrete, specific examples. And in this context, as we will see, really, to get concrete in the sense that we can really do all calculations explicitly, we'll turn to basically toroidal models, toroidal compactifications. Okay, and this is very special, but we will mod it out by discrete symmetries, which will give us orbifolds as concrete global examples, okay, of models that will have features both of standard model, namely gate symmetry, right chiral spectrum of three families, as well as replication, so three families replication as well. Standard model, and then I'll also talk about some grand unified models which happen to have the right spectrum associated with SU5, Georgia-Glashow grand unified model. Okay, so that will be the third lecture, and then so this already will be hopefully give us a lot of concrete examples of this, of how far we can get with the particle physics features in this framework. And then, I'll turn to real issues, problems, which will lead me to introducing non-perturbative effects. In particular, what I'm going to refer to now in analogy with D-branes, those would be the instantons. And I'll focus on the ones that will directly modify couplings of my charge matter. I'll highlight some specific ones, the so-called O1 instantons. And couplings there. Which, depending on what the fifth lecture will be, okay, how far I'll come, will be either issues of more general instantons, and in particular maybe some aspects of connections to type 2b of this framework. And not too ambitious, but that would be the hope. Okay? So in particular, those very, very rough notes that you have are basically building on some of the aspects of the last part of lecture. So I start with quantization of D-branes at the beginning as well. Okay. All right. So as far as references go, this part of lectures, so all the way to here, primary reference will be actually a review we have written almost 5 years ago with Brad Blumenhagen, Langacker, and Shiu. And it's HepTH. Along the way, I may mention some of the models, some concrete examples of standard and gut models. I'll refer to some earlier papers with Uranga and Shiu. Actually, that was the first example of three-family supersymmetric, globally consistent standard model example. And couplings calculation. So this is couplings. I will refer, if we really want to buy the bullet on CFT, I will spell out some of the things, but really technical details of CFT calculation of couplings in this context are in the paper coupling with specifically with Papa Dimitriou. 303, and also related work by Marchesano, Ibanez, and Cremades. So it's in the wrong order. So Cremades, Marchesano, and Ibanez. Okay. All right. At the same time. All right. So this is as far as topic 1 through 3 go, and then topics 1 through 5. Actually, for that we also have a review that came out early last year. So for these topics, really, a useful review is the review we wrote with Blumenhagen, Katru, and Weigand. Early last year. And this one really has a lot of, so really, in terms of getting better oversight as far as this corner goes and particle physics and then non-perturbative effect, those are the 2 reviews that are useful for your background. Okay, all right, so now let's turn to the spectrum in the presence of D-branes. Because the chirality will come again in a very geometric way. It's generally enough framework that we get chirality in a way that I can again draw a picture. In some T-dual pictures, those would be magnetized brane. It's harder to draw magnetic fluxes on top of branes than showing how chirality appears in this specific corner. So who has raised the question? Somebody asked me that. I was. Well, somebody asked me. I was answering the question. Okay. Yeah. You see, relationship to type 1 and type 2b is actually, in principle, straightforward but less geometric, because those are dualities that actually are not changing the strength of string couplings. So those are what I would call more perturbative dualities of string theory. So what we learn in this corner could be mapped in rather straightforward way to other corners. It's just harder to draw pictures there. Okay? So as a framework of getting particle physics with these D-branes, they are very much related. On the other hand, they are very different from heterotic string, which is fully based on closed string approach. Okay? So, all right? Okay. So what I'm going to deal with is with the presence of D-branes, where I'm choosing the D-branes as probes. Namely, as hyperspaces at which open strings end. Okay. So the actual quantized open strings describe weakly coupled gauge theory on such branes. So it's one limit, okay, of this, one side of the duality of describing D-branes. So the framework is example of taking D-branes as probes, so as hypersurfaces. Open strings end. And this is basically true for all type 2A, type 2B, and type 1 example. Okay? So we choose the hypersurface. Let this hypersurface extend in P plus 1 word volume direction. And we attached open strings to it, and they end on this hypersurface. So to get a spectrum associated with this word volume of this theory, we quantize open strings. So in this context, we get the spectrum action, but with boundary conditions such that the ends of open strings have Neumann boundary conditions on the hypersurface of the brane and Dirichlet in the transverse direction. And so this is pretty standard by now. So what we are dealing with is, so we are in 10-dimensional target space. So as far as bosonic coordinates, from, let's say, from 1 to P plus 1, we are dealing with the Neumann boundary condition. So this is, the sigma is 0, both at one end and the other end, so that corresponds to sigma equals 0 or pi. So this is the boundary condition on that set of string coordinate, bosonic string coordinates. And analogously for the transverse ones, let me call them J, where J goes to P plus 2 to 10 dimensions. We are dealing with the Dirichlet boundary conditions, so we can translate that technically it's 0 both. Okay. So when we quantize open strings with the specific boundary conditions, we would always get as a physical massless state an object that is spin 1 field. Okay. It's field associated with these excitations in the target space. So basically, those are string excitations that are bound to live on this hyperplane. And in particular, we would have gauge bosons whose vector index, okay, lives precisely on this hyperplane. So, if we quantize actually open string in this context, we could associate the physical state of this spin 1 particle. We can associate it actually the corresponding vertex operator, which is the excitation of a massless physical state that creates this gauge boson in string theory. We can write this in particular way in terms of the polarization vector, and then it will have momentum living only on this hyperplane. And as far as a string vertex operator in string theory, one way of writing it is with the Navier-Schwarz fermion, superpartner of this bosonic coordinate. So this goes now, let me call this a vector, polarization vector with this Navier-Schwarz fermion. And those familiar with quantization of superstring, this would involve also corresponding superconformal Gauss contribution. And this is actually vertex operator for this massless physical state in -1 Gauss, superconformal Gauss picture. So for those that are not familiar with quantization of superstring, that would be the whole separate set of lectures. Okay, I cannot go into it. For those that are familiar with that, I'll go in parallel, and I occasionally write things like this. Okay? Otherwise, you have to believe me on face value. Okay? As far as the mass of the state goes, why it's massless, it has to do with the fact that actually this conformal dimension of this particular vertex operator, and here I'm going to focus only on this part, so let me call that 0 part, is precisely 1. Because if its conformal dimension is precisely 1, then we see that actually the momentum square of this vertex of this field created now on the word volume is k square, ki is exactly 0. And so it appears as a state at the mass level 0. Okay. So this is just basically the appearance of massless state at associated with the gauge boson that lives on the brane. If we have n branes, we correspondingly can put n of them. Let's put them as hypersurfaces stuck together, and so let's deal with n of them. Okay. And now we have to be a little bit careful about the temp pattern factors. So if we associate the particular charges at the ends of the strings to end on each of these boundaries, let me denote this temp pattern factors with lambda a, and a goes from 1 to n. So we distinguish on which of the n hypersurfaces we end open string, and then we also have the other charge that the other end of the string ends, and let me denote that to be related to temp pattern factor that is exactly conjugate. It's associated with orientation of string, and that can also go from 1 to n. Okay. So what we see in this case is that we actually now can get n charges associated with one end and n bar charges associated with the other end. And so we get actually n square gauge bosons. So let me talk about indices A and B bar. where A and B go from 1 to n. And so we are talking about n square gauge bosons. So we are dealing with n square spin 1 particles associated with the appearance of non-abelian gauge symmetry UN. Okay? As a vertex operator that I wrote in this case, we have to carefully add also now the Champadon factors. So this is lambda A. So let me just, so I have to add Champadon factors. So we have here lambda A with lambda B bar. So we have to take careful care of the fact that actually those are charges tensoring basically fundamental representation of UN symmetry with its anti-fundamental producing the full adjoint symmetry. Okay, so this is trivial and old story. Okay, I'm not telling you much about it, much new that you already don't know, but I do want to mention even now, with this approach, we have basically geometrically see how in principle we can increase a particular abelian symmetry associated with the massless gauge boson on a single brane to non-abelian one when we put n stack of branes. Okay? So basically we already have building blocks even in formally this 10-dimensional theory of how to create factors associated with non-abelian gauge symmetry. Okay? So an intriguing new feature appears actually if we try to compactify such a brane configuration down to 4 dimensions. Okay? I have to do that. It's fine, with gauge symmetry that we reproduce in this geometric way, but our world is 4-dimensional, and I'll need this compactification to address better how chirality appears. Okay? So let me make a very brief digression. Okay? And reduce this theory on 4 dimensions, to 4 dimensions. Okay. Well, I already told you about a key massless part spectrum, right, that is confined to the D-brane. And so, for example, looking at the scattering of this massless gauge bosons in string theory, we can calculate S matrices and calculate couplings, how these gauge bosons couple to each other. Okay. Of course, they're going to couple in gauge invariant form. Okay, so we can get directly the lowest derivative term associated with the theory of gauge bosons, which will be of the type in 10 dimensions. Basically, it will be now an effective theory confined on the brane. So we have to just look on integrate over coordinates associated with the world volume of the brane. And then we have gauge bosons producing kinetic energy. And if we have, since we have now, in case of non-abelian guys, then that would just be associated with summing over the non-abelian gauge factors. Now the prefactor, okay? Now the prefactor you can in principle calculate, and it will appear because it arises from open strings as 1 over G string. Okay. And then on additional, because it's only string theory, open string theory, actually this effective theory is not, will involve string tensions, okay? And that will produce for us now the coupling that will be of the type, just bear with me, because I have to get the right powers. So this is confined just to the word volume, so to coordinates that live on the brain, and this would be related to, would have certain power of string, a string scale. Recall in the notation that I'm using, string scale is 1 over 2 pi alpha prime, which is string tension. G string is the coupling. It's open string theory. And now I have to get this factor right. Yes?
You're writing down the word volume?
Yes. Yes, indeed. Okay. Yeah, so that's when, and I have to get this factor right. Okay? So this should be now equal to, if it's p brane, it's p minus 3. Okay? So this would be this is actually the first term in what we call Bohr-Niemfeld action that we calculate in open string theory. But we'll get back to that. But this is the lowest term. That's the reason I want to use this one. I want to go down to 4 dimensions, okay, and try to get the right units, okay, associated with kinetic energy of this 4-dimensional space-time gauge bosons, okay, and related to string units and volume, okay. In addition, from closed strings, we will get gravitons as quantization. And of course, we would get also, doing the corresponding scattering of gravitons, we would now have the whole action coming over the whole space-time, 10 dimensions. This is I and J, right? The transverse and the one that is on the word volume. So this is the whole 10-dimensional space-time. And then we would have the Einstein curvature. And now the units would be such that this should be equal to m string to the 8th power divided by, because this is calculation in closed string theory, this will come with G string square. Okay, so this comes from closed strings, closed string gravitons, and scattering there, and this comes as the lower term in the, and this is confined on the, so this is now on the brain, so this is on the word volume of the brain, and this is on the whole 10-dimensional space. Okay? So this would be the contributions to effective action that we get both from closed string, lowest contribution, and from open string from gauge bosons. Okay? Now, we have to now go down to 4 dimensions. So basically, this is describing this theory of open strings living on the brain. But now we have to go down to Minkowski theory on some internal space M, which is 6-dimensional. Okay, down to 4 dimensions. Okay, and so we have to now reduce both terms down to 4-dimensional terms. Okay, so reduction of the gravity part is basically in a schematic way related to introducing the volume of this whole 6-dimensional space. So in 4 dimensions, this part of the action becomes d for x. This is our Minkowski space. With still the Kaluza-Klein reduction of this gravity, the part that are gravitons in 4 dimensions that I'm going to focus on. And then the rest become units, what we inherited from 10 dimensions, and then an extra part that has to do with the compactification of 6 dimensions. So let me call that as a volume in 6 dimensions. Okay?
Sorry,
yes.
I'm a little lost here.
Yeah.
So, the background that you're considering is a type 2A supergravity background? Like, I mean,
yeah.
Where are the proprints? What background are the proprints?
It doesn't matter really. It's DP brane. It's DP brane, okay? So I'm talking about now effective action, the leading part in the Bohr-Niemfeld action.
That's right.
Okay? And this is the closed string. Closed strings are everywhere the same. Okay, as far as gravitons go. Okay, as far as graviton goes, are everywhere the same. So what is key here that because these gauge bosons are stuck on branes, okay, those are actually excitations that are confined on the word volume of the hypersurface. Okay, so now when we do reduction down to 4 dimensions of this part, okay, what we do is we have to reduce only the part, you see. So what is really happening is we start with some dp brane, and we now reduce it to 4-dimensional space. Actually fiber, but let me just draw it over some 6-dimensional space, M6. Okay? 1, 3, thank you. So this is our problem, issue of compactification that I'll have to face no matter what in all string theories. But now with the D-brane, what I have is I have a D-brane. Now word volume of the D-brane has 3 + 1 word volume directions, and then there are p minus 3 word volume directions that are stuck on this internal space. So those are now some cycles of dimension p minus 3. So compactification, associated with the D-branes will involve D-branes, these word volumes, boundaries of open string in internal space wrapping p minus 3 cycles. Okay? So now we can envision this, that this reduction in this case now becomes just D4x. Okay? But now what we have is actually only part of this that is associated with the volume of the cycle in internal space. That's what not the whole 6-dimensional space that we encounter when we have gravity. So in this case, we have now M string, the inherited units, okay, and now volume of P minus 3 cycle, okay, and then the standard, the part associated with the standard 4-dimensional gauge bosons living in our 4-dimensional space. Yes?
So P less than 3, branes will be localized on M6.
Sorry?
For P less than 3, the branes will be localized on M6.
Yeah, I will look only at the cases of P bigger or equal 3. Okay? Because actually the idea with D-branes is that in our 4-dimensional world, we'll live on this brane. Okay, otherwise, I'm violating Lorentz invariance, and so definitely that. Good point. All right. So what I'm after is yes.
What is the problem in having it like D2 branes, for example? You can literally look at them as instantaneous solutions of the.
Yes, but those are backgrounds, non-perturbative backgrounds, right? As perturbative physical, excitations that we obtain in the background of D-branes, right?
Yeah, but you can also have D2 pro branes, exactly like you have.
Right. So you see what I'm calculating is in the pro-brane approximation, physical excitations, okay? Right. Massless gauge bosons, okay? And I want to connect this picture, right, of this massless gauge bosons to massless gauge bosons of our world, okay? So in this case, I'm pretty much stuck with that, right? All right, so this is now basically the 2 key terms. What we reproduce from closed string in 4 dimensions is ordinary gravity with Newton's constant coming from here, and ordinary non-abelian gauge symmetry with gauge couplings defined through that. Yes? Well, of course, yeah, there are scalars associated with the transverse direction, which are associated with this would be related actually to those would be moduli. They will be associated with the deformation of cycles in internal space. Okay? If cycles are rigid, those moduli are not there.
But moduli come from the global deformation, but those scalars will come from local deformation of the plane.
Right. So if I quantize to quantize the whole open superstring spectrum, we would have more states. Okay. And I just focus on gauge bosons. I even didn't focus on their super partners.
So you're just shooting to cut them off?
No, they are there. Super partners are there. Okay. They are actually also massless open string moduli. okay, which will be there and will be now in this compactification appearing, okay, as chiral superfields, okay, of the formations of the cycles. There are also other moduli associated with deformations that appear in the closed string sectors. Okay, so, but yeah, I'm simplifying some of it, right? So as I said, modular issues, whenever, will be, whenever we'll be confronted by them, would be in the context of connecting them to this particle spectrum. Okay, so right now I won't focus on them because it's enough to talk about just the gauge 1, spin 1, actually the whole superfield, and here the full supergravity thing. Okay. Anyway, what I'm after is about an intriguing possibility, actually, right? That through a lot of phenomenological studies, which has to do with the fact that now actually M Planck, by the way, I'm not carefully with 2 pi's, I'm not carefully with, but that Joe did very carefully in his original work and his book. So here I just want to give you broad strokes information. So we see that M Planck square that comes from here as 4-dimensional action is equal to M string to the 8th power, 1 over G string square, and then volume of 6-dimensional space. Okay. From here, we get 1 over Young-Mills coupling to be M string to P minus 3, volume of the cycle wrapped by P minus 3 cycle divided by G string. Okay? So let me, in particular, deal with specific combination. So you see the way we want to match string units, which are string tension and string coupling, and the volumes of internal space, is to map them to Planck scale in 4 dimensions, because that's our observed coupling, and to gauge coupling, which we can also measure if this UN symmetry were example part of the standard model gauge symmetry. Right? So those are measured things in 4 dimensions that we know, and actually we know what they are. We know that they are, this one is 10 to the 19 GeV, and this one is of order 1. Okay? This is to match it to real 4-dimensional physics. And as a consequence, we get that M Planck square times gauge coupling square is equal to, so M Planck square times gauge coupling square is, we have to divide that, and what we get out is that this is equal to M string square times V transverse times M string transverse over G string. So what is transverse? Okay? I'm going to write V transverse times V of P minus 3 to be 6-dimensional space. Okay? So basically, the volume transfers to 3, this P minus 3 cycle. Okay? So I'm writing the volume of 6-dimensional space in terms of the volume of the P minus 3 cycle cross transverse volume, right? Which is, and so using this combination, okay, we now see that this combination of M Planck and G Young-Mills is related to M string scale, string coupling, and the volume of the transfer space measured in string units. Okay?
How do we know G Young-Mills was order 1?
Because that's experimentally measured.
But, I mean, this is the coupling of some.
Right, but it doesn't run that much, right? Yeah, yeah. I don't think we are in the era of precision measurement predictions, so it's reasonable. For example, if we take standard model gauge couplings, they unify, I think, with 4 pi, what is it? G Young-Mills over 4 pi to be around 1 over 40 or something like this. Okay, that's more precise, thank you. Okay, right, and so, and you see, I wasn't careful with 2 pi's and all that, you know, I just want to give you the qualitative homework is to get all the 2 pi's right, okay, all that. But anyway, so you see, this is basically, this comes to the power of dimension of the transfer space. And so I can measure now, this is actually dimensionless quantity, this is measuring transfer space in string radia, string scale radia, right? And so you see, this gives us now a new opportunity, okay? Sorry? M string transfers, this is the number of transverse direction to p minus 3 cycle. Right? The volume is 6-dimensional. The volume wrapped by the p dimension is p minus 3. Okay? And this is the leftover. So if this is 6 brane, this is 3 cycle, this is 3 cycle. So it's 3. Well, M string is this one. So this is this thing. Yeah, it's the number.
It's a number, right?
Yeah, it's a number. Yeah, so if you want the real number, okay, this number is 6 minus p plus 3, okay? So this is 9 minus p, okay? So you want to be p 9 minus p, okay? So this was now kosher, okay? So anyway, there's a new chance now, okay? Typically, what we have in mind is this is of order 1, this is of order 10 to the 19. What we say is the internal volume, in this case transverse volume to the cycle, is of order 1 in string units, okay? Which forces us, M string, to be of order Planck, okay? So in particular, dealing with perturbative string theory, G string we cannot take too large. G string is of order 1 at most to stay within perturbative string theory, and then taking V transfers M string to 9 minus P to be of order 1. So namely, we're measuring the sizes in terms of string sizes. This relationship then forces us to take M string to be of order M Planck. And this is often generic situation, is the situation where we are forced to in heterotic string. Because in heterotic string, these gauge bosons come from closed strings. So actually our cycle is 6-dimensional cycle. So the whole story, when the cycle is 6-dimensional, we have no choice, okay? Because in this case, this is, so in heterotic case, we don't have this example, and we are forced, basically, staying within perturbative string theory to match onto proper units in 4 dimension. We are stuck with M string of order M Planck, okay? So this is actually necessary in heterotic string. But now with D-branes we have new opportunity, okay? Because we can in principle take the transverse volume, okay, to be much larger than string radii, okay? If we take the transverse volume measured in string radii, okay, much larger, then we can lower M string, okay? And that's a new opportunity, okay? It cannot happen in a heterotic string because we have no game. Nothing is here because, right? So with D-branes, whenever we have P smaller than 9, okay? So we have now, yes? Yes, I am stopping now. I want to stop now. So we have new chance, new possibility. When P is smaller than 9, now we can take this size of transfer space to be measured in string units much bigger than 1. And this allows us to match onto Planck scale with M string much smaller than M Planck. Okay? And so this is so staying still within perturbative string theory with D-branes, we have opportunity of lowering string scale at the expense of making extra dimensions much larger than the string radii. Okay? And actually, how far we can push that, if we take only one transverse dimension large, if we push M string to TV, this implies that then radius of the one extra dimension is in the millimeter scale. Okay, so there is a chance of playing this again, and that drew a lot of phenomenological studies of large extra dimensions. Okay, and lowering string scale down to TV scale. So avoiding this hierarchy problem between low scale where standard model lives and large scale, okay, while still having the right Planck scale. Yeah. Sorry?
Two transverse dimensions.
No. Then it's well, at least that's what I think. Well, one can put the numbers in, but I thought it worked only. I can check that.
I thought ADD was like 2. Is there some phenomenological?
Well, maybe there were other reasons, but we can put units in. But I thought I estimated that. Well, anyway, I think you can push it all the way down to 1 millimeter, but you cannot go lower. But I don't know whether it's 2 dimensions. I'll check that. Okay. Yeah. Well, let's see. 2. Okay. Now, so let me just finish this. You see, one has translated this problem of hierarchy between string scale and TV scale to the issue how to stabilize size moduli, okay, at much larger scale than this TV string radius. Okay. So this is, let me just say this, I'm sorry I went over, I really apologize. But the point is, so this is the spectrum of just associated with gauge bosons. So tomorrow we'll go with the spectrum associated with chirality, okay, and then global issues. Okay, any questions? Yeah.
No, why aren't you letting that the scale of 2D breaking at that scale? I mean, shouldn't that be the limit of how far you can push it? The scale at which you break 2D.
That's not necessary. Now, this is you see the scalar, this is vacuum expectation value. This vacuum expectation value is not necessarily the soft mass. Okay, but yeah, they could be. Sure. Yeah?
The weight is not just, I mean, that's not the only thing necessary, right? It should have some cycle which is very small.
Well, indeed, you can check that. The cycle is definitely of M string. It's of the same order of M string. But what is now possible is that extra dimension can be much larger than M string, and we can play this double game, lowering M string and increasing this extra transverse dimension. So they are much bigger than TV radii. Okay, so it's a game of low M string and large extra dimension. So that's an intriguing thing because that drove a lot of phenomenology, actually, observed just from the simple property of quantizing open string on the boundary. Okay. So as I said, tomorrow I'll do the chiral matter, how it appears, and then we'll deal with the global issues, okay, which are important. Thank you.